This is an indefinite integral. Oh, look at that! It's an indefinite integral. If you were cranking along and you weren't given any special integration rules for this, what do you think the most common incorrect answer is? If you were just cranking along and you had no tools to attack this, you might think that the integral of this is what? Anybody want to guess? E to the x or x e to the x or x. You know, people look at it and they say, oh, the derivative of e to the x is e to the x. The derivative of x is 1, so maybe it's x e to the x. So if you thought, for example, that the answer to this was x e to the x, how do you test your answer to see if that's actually true? You take the derivative. You would do d dx of x e to the x. What rule do you have to apply if you take that derivative? Product rule, the derivative of the first times the second plus the first times the derivative of the second, and you end up with e to the x plus x e to the x. And is that equal to this thing? No, it's not. Is there an extra little bit right there? Yeah, what's the extra little bit? E to the x. So you know what? Let's say, okay, if that's the extra little bit, why don't we just take it away, and maybe this is the answer. So I'm doing guess and check. I'm thinking to myself, okay, and I don't know why it's not letting me select this all of a sudden. There we go. Maybe instead, so this one doesn't work, but maybe this one does. So this is guess and check. Do I subtract it? Oh wait, but if I subtract there, it just becomes e to the x, right? So maybe I do this instead, and for some reason my stylus is being a little cranky today. I apologize. So maybe this is it. We had too much before, so how do we test to see if that's in fact the answer? Yeah, we take the derivative of this, d dx of x e to the x minus e to the x. So if I take the derivative of that, what rule do we apply to the first one? Product rule, so we get 1 e to the x plus x e to the x. Well, what's the derivative of e to the x? Oh, so does it actually work this time? Did we end up with what we want? We did. So is it possible by guess and check to do more complicated answers, to do more complicated integrals? Sure. Why isn't this guess and check method just going to work all the time when we run across other more complicated integrals? No, that's exactly what I'm looking for. They could get too complicated. This is about as clean as you get, because what is the derivative of e to the x? What's the integral of e to the x? What's the derivative of x? 1. This is pretty much as clean as it gets, so this is generally why you see this as a lead-off question. Now, can you do this one by guess and check? You can. You can try it out. But the problem is, again, what rule did we have to apply to check our potential answer right here? What rule did we have to apply right here? The product rule. We can undo the product rule sometimes in our head, but is it always going to be something we can just do in our head? No. There's the product rule right there. No, I don't know why mathematicians initially chose letters that look and sound alike. I don't know. If I took the derivative of something, how do I undo the derivative? What? Say it. You integrate. So let's integrate both sides, and you end up with uv equals the integral of this thing. You with me so far? The integral of the sum of two things, what can you do to that? Separate them. So you have this right here. And now I'm just going to subtract one of them. I'm going to subtract the one on the right, so I'm going to say uv minus uv prime is equal to the integral of u prime v. Now when you first see this, do you remember when you first saw this? Do you remember what your initial thoughts were when you saw this? I remember my first thought. My first thought was, like, why is this helpful? Because it looks like we took something that was relatively straightforward and turned it into something worse. Especially since, is there really much, like, you don't really care about this, right? You're more interested in this. So when you're looking at this, you're like, why would I, now could I put this one over here instead? Yeah, I could put that one over there instead, but it doesn't really seem to change much. Can anybody tell me what the point of this maneuver is? Why do we do this? The only thing that's really changed, honestly, is where this little derivative is, right? Y is rewriting this integral like this sometimes really, really helpful. Why is this integration by parts method really helpful? Why does that phrase help us? Your method revolves around, and this is usually this is how it's written in our book. They do uv prime, so it's uv and then u prime v. You can choose which one you want, but just be consistent with it. Again, I don't know why the letters were chosen such that they look alike and they're spoken alike. Yes, Umi. Yes, you could. Sure. Totally fine. Totally. Just be consistent with it, okay? It all comes down to what, though? So in this method, it's not always going to work, and there's going to be false paths, meaning paths you can take that are going to lead you to dead ends. The entirety of the success of this method revolves around your choice of what? U and V. Are there going to be multiple options usually? Sure. So how do you go about choosing U and V? These are three hugely helpful steps. Whatever you let V prime be, you need to be able to find the integral of it easily, right? Similarly, it helps if the derivative of U prime is simpler than U. Is it always going to be that case? Not hard. It's not always going to be the case because it's a subjective word, easier, right? But generally speaking, you want to pick something for U that when you differentiate it, it gets nicer. Nice. And it also helps if V is simpler than V prime, usually. These are general rules, and it just takes practice. So for example, first of all, what kind of integral is this? A definite integral. So you look at this and you're like, oh man, I should know this because, oh wait, it's not e to the x, it's ln x, right? So this is one of the first ones many people see in their life. So our first choice is, our first project is, we have to choose U, and let's try V prime. Anybody want to guess what we want to try for U? ln x. ln x works because, remember in that list of reasons why you want to choose U or V a certain way? Why is this a good choice? Yeah, it's just 1 over x. It's a nice derivative, exactly. And this one, if we choose this, what does it force V prime to be? Well, let's call it dx instead. It's 1 dx. Does that kind of make sense why that's the case? Yeah. So if that's V prime, what does that make V? X. All three of the things we wanted work. You know, we got simpler. It was easy to take the integral. So we know that this now equals U times V. What is U times V? Yeah, I'm putting the x first just because it's easier to write clearly. And then what do I subtract? We're going to use this one right here. So let's just use this. U times V times, so it's U prime V. So what's U prime? Yep. 1 over x, correct? And what's it multiplied by? Oh, and there's a dx right there. Oh, what's the magical thing that's super helpful? It's yeah, and we're evaluating this from 2 to 3, right? So what do we have here? X ln x times minus the integral of 1 dx from 2 to 3. But what's the integral of 1? X minus x. And we do this from 2 to 3. At this point, are you home free? Could you finish this for me? Can you plug in 3 and plug in 2? Anybody want to guess what U is? What we should choose for U? Anybody want to guess? We'll try ln x. So that's going to make V prime equal to what? X to the 6th dx. So what's U prime going to be? Dx. And what's V going to be? 7. So let's try this out. So U times V is x to the 6th. No, sorry, wrong one. U times V. So we have 1/7 x to the 7th times ln x. And what are we subtracting? X 1/7 x to the 7th dx. Is that actually kind of nice? Why is that kind of nice? Because of what? Yeah. And can you just integrate that? Yeah, you suddenly can. So you end up with 1/7 x to the 7th ln x minus 1/7 times what? Done. Look at that. We did it twice. So what were our initial? We really liked having u be x squared, and we liked v prime to be sine 4x. Sine 4x, what was it? dx? All right, there we go. And then you do it twice, and then you are happy. Nice. Very good. Okay, so many of you figured out that this thing does indeed equal, what is it? Cosine theta sine theta plus the integral of sine squared theta d theta, right? So you looked at that and you said, I told you you needed to do parts twice, right? So you look at that and you say, oh, what's the target of our attention now? Sine squared theta. You're like, oh, we just did it for cosine. So you do it again, but then what do you end up with? If you do it again, what happened, Matt, when you did it? It's itself. You end up with 0 equals 0. So that can mean two things. When you do proper algebra, you end up with 7 equals 7. What did that mean about the system of equations to begin with? It means like all the solutions work, right? But here's the thing. Did we start with an equation? Yes. Like basically you said that you just showed that this is true. Yay, right? But we're trying to rewrite it as something that is not just, you're not verifying that it's true. So yes, you have verified, if you do it again, that it is true. But we want to rewrite this as something without an integral. So let's rewind for a second. You did it right, Matt. There's nothing wrong with that algebra. Also, you might have actually seen it before. Do you remember when you did systems of linear equations and you substitute an equation into itself? Does everybody know what happens when you substitute an equation into itself? You get the same thing. You get 0 equals 0, right? So let's look at this again. Let's meditate on this. Our focus, everybody, is still this right here. This is our focus. Simple question. With many different answers, but there's one simple answer that will actually help us. What is sine squared? You told
us not to use trig identities.
No. That is not what I said. I said don't use trig identities where they're not useful. You are turning sine theta, cosine theta into just something else, which might have kind of been helpful if you went on this long journey through the mystical land of trig identities. I'm just showing you the nice way, okay? And I wanted you to run into a dead end. So, what can you do with the subtraction? Yeah, you can separate it. Plus this minus the integral of this, right? But what do you have on the other side? The same thing. So what can you turn it into? 2 cosine theta d theta is equal to cosine theta sine theta plus what? Theta! So what do you divide both sides by? The integral of cosine theta squared d theta is equal to 1/2 of cosine theta sine theta plus c. All done. I wanted to show you another cheat trick, which is sometimes you're going to feel like you're getting stuck. Because if you kept on doing this, you either get to this dead end of you verified what you did at the first step was true, and you're like, that doesn't help me. It's like doing the ratio test and coming out with 1, you get nowhere. You've done everything right, but you've got nowhere. This thing shows you that if you're doing something that seems to be oscillating, always think in your head, to get back to where I began, because then you can move the integral back over and then divide a constant out. There are very few cheap tricks with integration by parts, and you've seen 2 of them today. One of them is just repeated, if the power is going down, keep going. And another one is, if you see the same thing on both sides, put it over there and divide by the constant, and look, you get this nice answer. Okay.